visualization of the Okay, good afternoon. My name is Ibrahim and I'm a PhD student in, okay, I can say candidate right now in passport. That's last week. So, I'm presenting just one aspect of PCM. That's extensive work in our lab that we are doing with 20 more graduate students. And I am the only one that tried to use PCM as a side of my project. So that means PCM is developed everywhere. And I'm not doing anything on PCM, but using PCM property to integrate with other initiatives and make life easier and more comfortable with less energy consumption. So here I'm going to introduce a little bit PCM. Maybe it's not a good idea with also masters here, but anyway. And the model that I'm using is best test case 600, which is developed in ASHRAE for comparison. And I'm using chances 16, and then I'm going to give you the result very fast. And before, I greatly appreciate your presence here. All, okay? So, first of all, when you dig into the literature, PCM is used for three main reasons. And these are the reasons that always is appealing, right? Enhanced thermal comfort. Energy consumption would be reduced. Great. And of course, the reason is because it absorbs energy from the sun and releases it at night because of the property, phase change. And I start with this governing equation, and then as you see here, during phase change, we have a fraction that already changed the phase, and the other, which is simple integration. And as is convenient, one-dimensional result is good enough because in simulation we are uncertain enough. So fair enough to consider one direction. And of course, some assumption as this is constant and density is constant for sure. For sure, yeah, I can say. A little change, not that much. Again, in uncertainty. And of course, we can get this mathematical model, which is, by considering this, you can get a few different models, which I'm using effective CP as a base to solve this model. And end of the road, whatever is done by computer, for sure, I need this one, which is energy consumption related to H value. I call natural or free convective heat transfer as H value from now on. Okay? So let's see what's going on. What's the difference between phase change material, as you see, and sensible source. And this is the PCM, which is developed in Halifax University in Canada. And I'm using this because it's real. I don't mind, because I'm trying to consider the effect of H value. So whatever PCM is the same in all simulations. So why PCM is doing what that we love it, that's the reason. As you see, ambient temperature during the day, and of course the other side, solar energy, PCM gets the energy from the sun during the day and shifts it to the night, and the result is demanding dust fluctuation. And if you consider this as set point, perfect, so we don't need that heating, cooling. So, back to best test. These are the properties that I have to input to the simulator, which is chances 16. Having said that, Transys doesn't have PCM, so I had to take a model or a module for PCM. And out of lots of modules, I preferred Helsinki University module type 204, which I like it because mathematical model is so touching. I can feel it. It's very good. I can see that. So again, whatever it is fixed. I'm just changing the H value. And again, roof and floor layers is all given to the Transys. And the question right now is, what is the H value range? So again, back to literature, thanks to all researchers, I found experimental H value could be something between 7 to 10.5-ish, something. And so I decided to get the H value from, of course, less than 1. It's not meaningful in building science, but for sake of simulation, it's not bothering sometimes maybe. Later on, somebody can use the data for, I don't know, space, to do convection. So this is the range selected, and then I started to make the module and do PCM. As you see, this is the type that is developed in other university, and these are all modules taking data from Toronto weather condition, radiation, and temperature, humidity, and these are all conventional way and making the layer by layer. The job done, and then the output. The energy is this range which I'm concerned about, and this is the temperature range which is set point is 21 to 24. I guess, yeah, and this is the fluctuation of ambient temperature. So another point, we are solving differential equation, and not always we can get exact solution, for sure. So another decision I had to make, how many iterations should I go? So it's, again, another curiosity, and it took me 50-day computer time to come up with kind of reasonable answer, which shows I started from iteration number 1 until 20, and I could get this regression, which is, again, makes sense. And yeah, I decided 3 is good enough because it's 5% uncertainty. Engineering, fine, 5% absolute good. So, back to result right now. What's the result? The effect of H value on cooling energy demand. In Toronto, mostly we have heating. But sometimes cooling is important, not always, and it happened to over 4,839. I guess it's somewhere in August. Yeah, no, sorry, it's here. The 5th of July. So, at the time, temperature outside was 31.11. And I changed the H value, and you see with 2 different thickness of PCM, which is 1 millimeter and 10 millimeter. Not that much difference because it's 1 hour. So definitely I cannot feel that change in thickness. And this is, of course, not an issue because it's not PCM here, but as a comparison, I just dropped a few points without PCM. This simulation is drastically fast. But with PCM, I checked 1 hour. I started with hottest time, and then checked the cooling energy consumption in August, which is hot season in Toronto. And as you see right now, there is a gap between 10 millimeter and 1 millimeter. Of course, as a minimum, PCM is a mass, so thermal mass can make it possible. Less energy you need. Of course, we have to pay PCM. And the thing that I'm seeking for is a trend. almost for 10 millimeter, there is no change in energy consumption, so it's not sensible to H value that much when we have enough PCM. But when we have 1 millimeter PCM, yes, it's just positive correlation. Back to whole year cooling load, which sometimes can give us better idea. But I don't see that much change, trend within 1 month and 1 year. So to check the heating, which is dominant energy consumption, I guess in Toronto we have 60% of energy goes to heating. Again, 10 millimeter PCM, a slightly positive correlation, and 1 millimeter, almost same trend. So, conclusion is there, I guess. First of all, I repeat that I use this Ashrae-Vestes model as a comparison for all simulation. And 2 different PCM was used, 1 millimeter and 10 millimeter. There is no real, idea why 1 and 10 millimeter. I cannot tell you anything, because as engineer I always ask why. But 1 millimeter, 10 millimeter is because of our past experience in my lab. I checked out of them, I found extreme 1 and 10 was too extreme. So, more than that, sorry. And simulation I conducted inside H value from half to 10, of course, as I said, less than 1, but meaningful, less than 2 model. But I did it in terms of the condition, it's set point 21, 24. Without having set point, there is no demand, of course. And generally, increasing the amount or thickness of the PCM layer reduces the energy demand. In summary, by increasing H value, the energy demand slightly decreases. In slightly means just 5% uncertainty, so not that much important. In winter, energy demand is sensible to H value with positive correlation, and you know why it is this way. Because in winter, outside house minus 20 or something like that, and when you increase H value, you give a chance for conduction, so you need more energy conversion than more than getting in. So that's the reason. And additionally, I can conclude that PCM brings more benefit in winter than summer in terms of energy saving in Toronto with this model. And I would like to thank the supporter of the project and CERT Canada, and this is somebody from Canada, Agropol.
So what's the melting temperature range of your phase change material?
Sorry?
What is the melting temperature range of the phase change material?
21. I guess I can go back and...
So that's the same as your room temperature set point?
No. 21, 24 is the set point. I guess it was 22. Let me check. It was something between the set point. Okay, I can go back to this. Here we go. 22, 23. And I have another paper that proved this is the best range. And I still am working on parametric investigation if the middle of the set point always is the best. So this is another one, yeah.
And so does your room temperature go above this?
Of course.
Daytime?
Yeah, that's why we have energy. Otherwise,
Yeah.
demand means
Just to check.
touching the set points up and down. That's the demand mathematically. And this is all mathematical. No idea here.
And maybe can I just do one last comment? Yeah. That's quite a gap between 1 millimeter and 10 millimeters because the phase change doesn't conduct heat very well. So you might find that you don't actually access.
Conductivity is not good. Yeah.
You might find that you don't actually access the heat capacity of the phase change further than a few millimeters deep into the phase change material. In reality,
we know that. Actually, it's not because I'm from other space. I checked the literature, and I'm developing another project that solves this problem using heat pipe, which solve this problem. Integration, that's my job, as I said. Heat pipe with PCR, perfect. Yeah?
I think you mentioned about the energy, the heat load, the cooling load is not dependent on the hatch. I think that this should be not calculated because this is just yearly energy consumption. Because the convective heat transfer coefficient H just affect the probably hourly. If you're doing hourly heat release, heating load or cooling load, that will be different. Because for long run, you totally have that total heat fusion. Your potential heat that will be released totally. So in the long run, for the yearly energy consumption, it won't have any effect at all. So if you just doing some hourly, that is instant energy consumption, definitely it will have some effect. So that's my.
To be honest, I went in reverse. I had the result of 1 year. I dropped to my supervisors and discussion. They said, okay, dig into detail, see what's going on. So I went to the months. They said, okay, not good enough. I went to the hour. We couldn't go lower than that because 300 was time step, 300 seconds. So yeah, again, if you know the problem, you can seek for the solution. We had a problem because right now, solar energy is there. We are thinking maybe a fan under the wall can help because we have lots of work in PCR. Maybe it works and give us a better idea, but not really.
But the convective heat transfer has definitely will affect the instant. If 1 hour reduction maybe needing something, definitely will affect. Because let's say heat exchange between the PCM and the air. If long run, it won't affect. That's true. But for hours,
One final question.
Yeah, I think there's quite a lot of connection with the former speakers that dealing with pitching material. And the former one very interesting result is that despite the load summation for 4 years, it's not really significant improvement by using the pitching material. But if you change another side by how many hours discomfort, so that will be greatly improve the condition. So maybe if we evaluate the system material, it's not suitable using the load for 4 years as the evaluate value, especially using the how many hours discomfort higher than what kind of temperature or lower than.
I think it should be either greater hourly energy consumption in just some motion.
Yes.
It should not, if you do it averagely, it does not make sense.
Because the pitching material is also another
very important for
passive way
Yes.
to solve problems. Maybe that's
true.
make the indoor climate more.
I would ask two final votes, one for our speaker and one for the two people in front of us. 3 days and one for the other.